We now move to an excitement segment of the day, the student competition. This year, we bring together some of the brightest minds presently enrolled in their MTech or Master's second year, presenting innovative ideas in earthquake engineering. But first, I would like to extend a warm welcome to our jury members who bring immense expertise and experience to this session. We are honored to have with us Dr. Shilpa Paul, Professor Civil Engineering Department, Delhi Technological University, and Dr. P.C. Ashwin Kumar, Assistant Professor, Department of Earthquake Engineering, IIT Roorkee. So our first student presenter is Samved Patel from Department of Civil Engineering, BITS Pilani, Hyderabad campus.
Shall I start? Yeah. Good afternoon, everyone. I am Samved Patel. I am from BITS Pilani, Hyderabad campus, and today I will be presenting an analytical study on twisted high-rise buildings exposed to dynamic loads. As soon as we see this picture, it's a twisted high-rise building. It's an architectural marvel, right? So it's an architect's vision, but at the same time it's structural engineer's ingenuity which gives the life a structure, which gives us a resilient iconic structures. While designing these structures, it's important to know the challenges faced. I came across Evolution Tower. This image shows is the Evolution Tower, which is in Russia. It's a twisted high-rise building. And challenging faced can be complex lateral load resisting systems or irregular resisting systems, or maybe torsional irregularity. My main objective of this study was to analyze how a twisted high-rise building can have a different load resisting system such that it can inhibit a structurally stable as well as dynamic amplifications on that structure. We will deep dive into it in a while. Giving a brief introduction on my structure, which I have analyzed, is a 55-story, 3 meters of height of each floors, and just for sake of seismic zone, I have chosen a zone 4, having a zone factor as 0.24. And as you can see, there is a central shaft for a shear walls. But if you observe here, the only part which is constant are the central portion, while the exterior part is being getting exposed. So central part is rotating by 3.67 degrees on each floor, and that's how the geometry is being designed. Coming on to each floor, this is what the structure looks like on each floor. If you observe, there is a central circular columns, and exterior columns on the 4 edges are rectangular in shape, which are beam, column, and slab grids. To analyze this structure, I have used static as well as dynamic load. Static loads consist of dead loads and alive load of a structure. Along with that, earthquake load has been assigned as per statically as per IS 1893-2016, and dynamic loads considering L centro data. So main objective of this study was to figure out how a story drift or a story displacement of the structure can be optimized in such a way that the best optimum solution can be obtained using least cost and a least seismic weight. So as you can observe, model 1 is I have considered as a base model, and the red highlighted are the shear wall positions. From model 1 to 4, shear wall positions has been strategically placed such that it has the minimum eccentricity along with the stiffness of the structure has been distributed equally. If you observe the model 5, I have also introduced steel bracings such that energy dissipation can be provided in a better way along with shear walls. So that's about the configurations. Now what was my study and my observation will be giving you results brief as well. The main objective of this study was to define least story displacement accordance with the IS 1893 standard, which is 0.004 of story drift, and allowable displacement, allowable drift. Along with that, the seismic weight having the least configuration would be the best option. Coming up to the results, as you can see on the left side bottom, it's the story displacement. When we multiply 55 stories having each floor says 3 meters, we get 660 mm of story displacement, which is allowable. Only model 4, 5 and 6 were the passing criterias when we observe the displacement, but at the same time the story drift on the right side shows model 5 and 6 were the allowable limit for 0.004 of story drift. Along with this, as I mentioned, this building is a torsionally irregular or not, it's a twisted building. So I analyzed center of mass and center of rigidity of each floor, and I came across a result that eccentricity was minimum, or we can neglect in such a way as per clause 7.1 by IS 1893, and can be concluded that it is not a torsionally irregular building. Coming up to a relative cost, which is like one of the major parameter in defining the best or the optimum configuration for designing a structure. As you can observe, model 1 has been chosen as a base model having 100% relative cost, and if you observe model 5 having 128%, which is 28% of increment in cost, but at the same time model 1 was having 7.7 meters of story displacement. At the same time, it has drastically been reduced to 322 mm, which is allowable as per IS 1893 again. And story drift was reduced from 0.01 to 0.004 or under as per the clause as well. So concluding it, while we figure out the torsional irregularity of the structure, a balanced stiffness distribution and controlled torsionality are the major parameters when we focus on high-rise buildings or say a torsionally irregular building. But at the same time, not much increase in material strength would lead to stability of the structure. Recommendations are shear walls can be placed away from center of mass, which will again increase the lateral stiffness, but at the same time will reduce displacements. Also, as I mentioned, that shear wall positions should be in such a way that it doesn't increase the torsionality, such that it needs to be placed symmetrically. And last but not the least, shear walls should be integrated with steel bracings such that it can enhance both stiffness as well as the energy dissipation of the structure. That's how what I analyzed, and these are my recommendations for the project. Thank you so much for the presentation. Thank you. I look forward for your questions. Thank you.
Well, thank you, Samvad, for your presentation. Very nice to see our MTech students doing this much of work.
Thank you.
So I have a few queries that I would like to ask you.
Sure.
What was your approach? Why did you select the shear wall and the steel bracing as an approach to solve your problem statement? Why was your approach only of the shear walls, and then in your model number 5 you introduced another retrofit measure, that is the steel bracing? So what was your approach towards
Yes, coming up to different lateral load resisting systems, I may have used base isolation, but at the same time high rise buildings won't much affect or much increase the proportionality of stiffness of the structure. At the same time, pendulum was not a major outcome when it comes to the twisted high-rise building because of architectural requirement. That's what shear walls was integrated with steel bracing such that the energy dissipation of the structure can be integrated maybe by increasing the isolator or integrate steel bracings can be integrated with isolation on different floors, which can be an option. That's what steel bracing was introduced.
Okay, so before you approach this problem statement, so you must have gone through the literature review.
Yes.
So can you tell me the base, the research paper based on which you identified the gap of the study and you identified the objective of the problem?
Yes. I can switch to. As you can see in this structure, the central portion was only having the the central portion was only having the circular columns, but due to architectural requirement, the exterior part, which I mentioned, that center of mass can be distributed equally on the center of mass should be on the lateral load resisting system should be such that it is been distributed equally as possible, such that the stiffness of the structure and overall performance of the structure can be increased.
Are you aware of the IS code which deals with the tall structures?
Yes, 13600.
No issues. Over to you, Dr. Ash.
No, I just have one comment. Sambit, you have done, MTech, you are in third semester.
Yes.
Third semester. So we should not critically assess them because during our MTech we didn't have such a competition to participate for. So this is a good initiative from Hilti side and you have done a good work. There is more to improve. Let's give them a round of applause. Thank you so much.
Second student presenter is Abhir Dutta from Construction Engineering Department, Jadavpur University, Kolkata.
Hello everybody. So, myself Abhir Dutta. I am the Master of Engineering student from Jadavpur University, specialization of structural repair and retrofitting engineering. And my topic is nonlinear static and dynamic analysis of NG-type overhead reservoir on frame staging. So, voucher is a critical component in the water distribution system to supply water with a sufficient pressure from a certain height. And the NG-type water voucher is one of the most used in practical purpose on frame staging. As per IS 1893 Part 1 2016, more than 60% of our country lies in seismic active regions. The Jal Jeevan missions aims to provide the water to every rural household, including those the seismic active regions. So, in the past earthquake like Bhuj, Jabalpur and others have catastrophic failure in vouchers. Thus, the seismic vulnerability should be checked for the ensuring the safety purpose against these earthquakes. So, we can done the comparative study of the performance, and the numerical models are developed as FEM based SAP 2000 for nonlinear pushover and the nonlinear time history analysis, followed by IDA. IDA means incremental dynamic analysis for the real life seismic strong ground motions. And finally the fragility curves has been developed for evaluating the probability of damage as per FEMA 356. So the numerical modeling, the problem is to be three types of NG type vouchers are considered: 300 cubic meters, 600 and 900 cubic meters. There are several linear elastic analysis as per Hausener's two-mass modeling, non-linear pushover, and non-linear time history analysis followed by incremental dynamic analysis. And the fragility curves are developed for the different performance levels. So there is the structural details of the different vouchers as it is. Next, the numerical analysis, that is Hausener's two-mass model, the well-known just theories. The equivalent two degree of freedom system based on the Hausener spring mass model we have first considered for calculation the lateral stiffness of the staging. Then finally we have done the Hausener two-mass model for giving the impulsive and convective modal mass for getting the design base shear, and we can get impulsive time period and convective time period in the decreasing and increasing order with increasing the voucher capacity. Next, the structural drawing and the numerical model which I have done in SAP 2000. I have done it. Next, the well-known non-linear pushover analysis. From the top right corners, the typical pushover curves, the ultimate base shear capacity are the multiple corresponding linear elastic design capacities, and the top displacement are getting from the performance point. So the capacities of 3000 cubic meter vouchers are 4.26 times, 600 cubic meters 5.85, and 900 4.2 times. So it shows that it seems to be 600 cubic meter voucher have greater performance. The higher capacity vouchers are seen to be greater flexibility, higher global stiffness, higher global ductility, and the safety margin of the against maximum considerable earthquakes. So the comparison graphs are there. After that, I performed the third one, non-linear time history analysis followed by IDA. So with the four well-known earthquake waves are considered, and we are getting from Pierce Pacific Earthquake Research Center. They should be scaled by the Seismomass softwares to represent the range in the realistic earthquake intensities. So the scale factors should be peak ground accelerations of target response spectrum to the peak ground accelerations of actual earthquake data. So the Great Mexico, Bhuj, Nepal and Turkey, the four earthquake data should be matched with the response spectrum curves and the scaled acceleration we are getting from. So the intensities of the each ground motion should be incrementally increased as 20%. That means in the chart I have shown 0.2G, 0.4G, 0.6G, that's why, and corresponding the drift ratios are to be obtained. Intensity measured IM as considered as PGA of spectral acceleration at the first time period, and the damage measured as the maximum drift ratio. As per FEMA 356, the collapse prevention 4% of maximum drift ratio should be permissible. So the base shear capacities getting from the left corner graphs, that is base shear of IDA is less than the base shear of non-linear pushover. And the several four types of IDA curves are formed in the right corners. So we have getting from the previous slide, the IDA base shears are critical. So we analyzes the fragility for the IDA base shears. So this is probability of damage exceedance, which are given by Sekarzami and Rofi. That is the probability of ln xi minus lambda divided by beta, where beta is the standard deviation which are performed by the right side table, and fragility curves of the typical Weicher capacities are shown below. Next is the fragility analysis at different damage states. That means immediate occupancies, life safeties, and collapse prevention. At the immediate occupancies, we have shown that the curves are very close to each other, and the life safety is well separated, and at the collapse prevention state, the graphs are more separated and less sloped. That means flat slope. So the concluding remarks it contains is two-mass modeling provides a greater design safety for the smaller capacity Weichers, where the nonlinear pushover and nonlinear time history followed by IDA are great result to tuned, and both the performance for the higher capacity Weichers are greater. And the pushover is computationally economical, less time taking, but the IDA is more realistic and accurate. The flat slope of the fragility curves indicates the low rate of fragility increment at the higher performance level for the higher capacity. Thus, the nonlinear analysis is recommended to ensure the greater safety and making resilient public infrastructure. And future scope you can include for IDA, you can include fluid structure interaction or soil structure interactions. You can include the numerical studies or the alternative staging types and heights with the probabilistic approach. There is some references. So thank you.
Thank you, Abhir. You have done a huge volume of work. Only one question from my end in terms of the base shear, design base shear versus the capacity that you are achieving. Based on the fragility analysis, can you enlighten the audience about whether we are over-designing our INSI tank?
Obviously, sir. I am workable as a junior engineer in public health engineering, West Bengal Public PhD department. Most of the case, our planning departments are seems to be that this is the low capacity soil, so you can recommend a low volume of Weichers. So this is kind of joke. Why? The design base shear for the lower volume of capacity Weichers has greater performance at the design performance level, DBE, design basis earthquake. If you consider the maximum considerable earthquake MCE, then you can get the higher capacity Weichers performs better. For the same region, same soil structure, soil conditions. That is the most important things. And we have decided that where the 300 cubic meter Weichers are constructed, then further for new sites, we have decided to get more capacity Weichers. That means around 500 or 600 cubic meters. It should be more beneficial for our governments, our public sectors, and infrastructures.
Okay, thank you, Abhir. I'll also like to ask you the very basic question. What is a fragility curve?
Fragility that means the probability of damage exceedance. It represents how a structure becomes more fragile.
Can you go to that slide, the previous slide?
Okay.
For the three curves you have.
Sorry. Yes.
So you
That
said that in
means-
your first curve you have very
Yeah.
बड़े पास में है, फिर वो दूर में है. What does it
हाँ,
actually
हाँ.
tell us?
That means immediate occupancies is achieved at earlier stage. So immediate, as per FEMA 356, we have studied that 2% maximum drift ratio when the structure achieved, it is called immediate occupancies. So very close in you can't identify each structures at immediate occupancy levels. So मतलब थोड़ा थोड़ा डैमेज हो गया, हेयर लाइन क्रैक्स आ गया, तो that's why you can don't judge the structures at these levels. The main part is life safety. Life safety means our life preventions. ठीक है, so that's why the green curves, that is 300 cubic meter curves, that is that affects the first the earthquake effects. So smaller capacity vehicles get affected at the faster time earlier.
Thank you. That's all. Thank you and well done and all the best.
Thank you, Abhir. For third student presentation is by Sema from Earthquake Engineering Research Center, International Institute of Information Technology, Hyderabad.
So good afternoon everyone, and good afternoon jury panel and my colleagues and everyone. Good afternoon everyone. Today I am here to represent and to show my work under the AI driven seismic vulnerability assessment tool. So nowadays, like I think everyone is aware of earthquake, how it will affect the building and how damage will occur. And as a structural engineer, we are focusing on the safety, and we are focusing on the life loss, and we are focusing on the financials and everything. But so nowadays, but we can't go for each and every structures, because it's in our country there are so many buildings, and around the, as our sir mentioned, like there is a 13 crores of buildings, 13,000 of crores of buildings are there. So but as a structural engineer, I can't go to each building and I can't assess each and everything in a short period of time. But in this AI generation, the AI tool will create the with this tool we can assess the structure within a minutes, not within a minutes, within a seconds. So see, this is a tool. It is not just a tool. If we train the AI, it will become as a lifeline also. So, and this is tool not used by the not only the structural engineers or the civil engineers. It can used by the public also, who are not even the civil engineers. So, but let me go into the see, as a subtitle I have mentioned, the teaching machines to sense structures weakness before the shake. So before the shake, like before the earthquake, we are assessing the structure, we are assessing the structure, and to know the how much the seismic vulnerability of a building is happening after the earthquake. So let's move on to the next slide. So in this tool, I have focused on the three cases, majorly the short column effect and the crack and the soft story buildings. Why I have chosen these three cases? Because see, as a civil engineers or any other people, they want to construct a open story building, because why? They need a parking place, right? So we can't park our cars or bikes in any other leftover ground, but we need a separate place in our building. We are creating an open story ground. So there are so many buildings of the open story ground, but these open story grounds will affect more during the earthquakes. And the next one is the crack. Crack is a very like regularly seen thing, very regularly seen vulnerability in the buildings. Anywhere we can see the crack, right? In the column we can see, in the structural walls we can see, in the beams and the columns, every structural member has a crack. But again in the short column, why the short column effect? See, as a architectural view, they prefer the short columns, not the tall columns. And these three cases will affect more during the earthquake in a building. So I have focused these three things, but in later my further work, I'll focus overall building, how there are all the vulnerabilities to detect by the AI tool. So how I have trained my AI tool. So first I will go for the AI detection. So first I will input that. So I have trained that. So this is the crack. So this kind of cracks, wherever if the user has posted anything in a building, you need to first assess the crack. So it is in a diagonal, or it is what is the crack width and what is the angle of that crack. So it will based on that requirement things, it will detect as a crack. And the same thing for a soft story also. Based on the aspect ratio, it will determine the short story. And the parking area, how much the area is open. So based on that, it will detect as a soft story. And same for the short column also. The thickness and the dimensions of the column, based on that, it will detect the short column effect. So this is the input. This is the input of the AI tool we have given. And later, so as I am a structural engineer, I want to put the tool as a structural engineer validation. So how I can assess that this tool is giving the correct detection or not? How I can guess that? So by engineering validation flowchart, it will take the from IS 13920, IS 1893, IS 456 and some American codes. We have, based on that, we created some checklist. So based on the checklist, it will show the how much vulnerability is happening. So as a structural engineer, by showing the checklist, so we can tell it that yes, the tool is detecting the vulnerability is correct. So and I will show this tool also, what are the requirements we have taken as a checklist, we'll show here. And this is the performance matrices. Like I have detected this flowchart. It shows that how much percentage I have required for the accuracy of 86.5% for the accuracy. But for the soft story buildings, 92% of precision, and for short columns, 84% of the precision, and for the diagonal crack, 83% of the precision I got by the AI tool. So, and this is the graphs how this AI tool is trained. So as you can see, this the graph is starting from the top and it is coming to the lower. That means we are trying the tool is correct. So if the curve, I mean if the graph is not coming to the downwards, it is going to the upwards, or it is a neutral line, then the AI's detection is wrong. So based on this graphs also, detection also, we'll find out that the AI tool is detecting the vulnerability is correct or not. So this is what, and I will go. Let me move on to the AI driven tool, live tool. Okay, so this is the AI tool. So as you can see here, this one is the input building image and one is the AI detection results, and we based on the some particular things it is assessing. We are using the IS codes and international codes, ASC 76, and these all are the requirements. And as you can see, these are the checklist we have made for the soft story and the short column and the diagonal crack. This is for the checklist. So let me post an image here. So I will post an image, this thing. Just a minute. Yeah. As you can see here, as a structural engineer or a civil engineer, we know that it is a compression failure and it is having the diagonal crack also, right? So we can assess that. But how the tool can assess? So by clicking on the performance engineering assessment, it will detect. So here, as you can see here, the percentage also is given 0.99. That means it's a 99% of the accuracy. And you can see the report also. By seeing this report, you will get a full of clarity that how much vulnerable the structural member is getting. So in this thing, we have seen some diagonal crack. So it was detected by the AI tool. Okay, with the confidence of 99.5%, and the risk level is very high. Obviously, it is very high. So, and the remaining thing was the checklist, whether it is satisfying or not. Whether if one thing is not satisfying, then it will come onto the risk level. Okay, and the next thing is, yeah, these are the codes I have mentioned, and everything will be coming into this picture. So how much percentage it is detecting by this report. So finally it will give the overall structural assessment. So yes, obviously it is required some retrofitting things or structural assessment is required. So we should contact to the structural engineer, professional structural engineers, and make it the structural retrofit or re-strengthening it by required methods using for the retrofitting everything. So this is how I can conclude my presentation, how this AI tool will help us to detect some vulnerabilities in a building. It will make our work very easier. And I hope that in my further work, I'll focus on complete buildings vulnerabilities and to give a proper requirements and the proper detection of the vulnerabilities with the percentage of the vulnerabilities. And thank you so much for everyone who are here, and thanks for your time. And any questions? Thank you.
Sema, great presentation.
Thank you,
But
sir.
just a comment in terms of the things that you have presented is key. Your work can be divided into two parts.
Yes,
One
sir.
is to check the vulnerability part, and
Yes.
the second part that you have shown as a picture is post-earthquake assessment kind of a work.
Yes, sir.
You need expertise in terms of understanding what failure looks like
Yes.
post-earthquake, so that it is not mixed with any other type of failures that is there. And one is the pre-earthquake vulnerabilities that you have to mix it with drawings.
Okay.
That is also there. Having soft story parking doesn't mean that it is soft story,
Soft story,
because
yeah.
our good
Yeah, yeah,
engineers would have already done that due diligence in terms of getting the stiffness worked out.
Yeah.
So try to incorporate the design details if it is there.
Sure, sir.
If
Sure.
it is not there, you can point it out.
Sure, sir. Sure.
Good work,
Yeah.
Seema.
Thank you, sir. Thank you so much.
Thank you, Sema, for your presentation.
Thank you.
What was the database that you have taken to train your AI system?
We have taken the images, ma'am. So we have taken the thousands of images for each cases. So based on that images, it got trained. So, and we are labeling that also. Based on the labeling, by using the software, so it's not a software, it's a tool which is used in the Python called label img. So in that we label that particular, it is a crack. This kind of thing will be labeled as a crack. So based on that labeling, it got trained and it is validated also.
So how did you validate that?
So based on the validator is by checklisting validation, and the whether it is the as I shown in the graph. So
What is the level of the confidence that you have with respect to the training of your AI tool with the data set that you have given?
the data is just completely depends on the images, ma'am. We are not taken any, but posting of an image, we can't know the size of that column, and we can't even detect. We can't. So if you want to train a tool with all the geometry aspects and the stiffness, we can't. We need a very big, huge data set also. So that's why I focused on the geometrical part and the how the easy can assess that structure. That's it, ma'am. But I could not take any data set. Only the images I have taken the data sets to train that tool.
Do you define the crack as a vulnerability? Like in your vulnerability, since your title is a vulnerability,
Yeah.
and crack has been taken as the vulnerability. Does it come under the category of the vulnerability? Do you understand what is risk?
Yes, ma'am. Yeah.
So it's a multiplication of what?
It's a hazard and exposure and vulnerability.
So how do you define vulnerability? So does the three parameters, out of the three parameters, okay, the short columns, the floating columns, other things are the vulnerability. Does the crack come into the vulnerability part?
But
The
it
three
is-
parameters that you've taken.
But it will affect to the structure, no, ma'am. It will lose of the strength. It will lose the stiffness, and the strength of the structural member will be reduced based on that. Crack has not the huge of the vulnerability, but it will some effect of the for the building during the earthquake also.
Thank you so much, and wish you all the very best.
Thank you, ma'am. Thank you so much.
Thank you, Seema.
So I think
Till the results
we
are-
can discuss for 5 minutes. In the meanwhile, you can play
Yes,
the video which has been sent by Sanjay Pantji, and then we can declare.
Good morning to all the participants of the event Building Retrofits Breathing Life into Existing Structures. First of all, I congratulate the organizers for taking this important topic for today's event, particularly from the point of view of Bureau of Indian Standards, the standards that we formulate. This is the golden period of standards or standardization in the field of structural design of buildings and other structures. Particularly considering the topic of the day, I would like to highlight that BIS has taken up a massive project of revision of earthquake related standards. IS 1893 on the criteria for earthquake resistant design of structures is on the advanced stage of revision, with part 1 on general provisions is likely to come out very shortly with the revised earthquake zone map of India based on probabilistic seismic hazard analysis. And similarly on part 5 buildings is also ready for release. And there are other parts which will come in 1893 series on water retaining structures, bridges, industrial structures and stack-like structures. We are also working on steel towers and coastal structures. Similarly, analogous to these parts and sections within the parts, for example, I'll say within part 5 buildings, 1893 is going to cover the criteria for design of earthquake resistant structures in different sections within part 5 for concrete structures, for masonry structure, for steel structure and so on and so forth. And similarly the ductile earthquake resistant design and detailing, on ductile detailing, the corresponding parts and sections would be covered under 13920, giving the ductile design and detailing for each of structures. For example, part 1 will remain for general provisions, part 5 would be on building, and there will be similarly other parts, so that there will be complete coherence between 1893 and 13920. As you know, the structures keep on aging or may fall short of earthquake resistance in their capacity, and therefore 13935 series is also being updated with similar parts and sections covering earthquake safety assessment and retrofitting of structures, starting from part 1 general provisions, then structure by structure in different parts and sections of the same. So in fact, this is to say that a series of set of standards would come up shortly for the civil engineers and particularly structural engineers to take their design to a higher level, bringing robustness and safety in earthquake resistant design of structures. And I'm also very happy to share that the revised NBC, which is also being prepared for release at the earliest, is also covering all these details in a very integrated, interwoven manner, so that the authorities concerned, the building professionals, the educational fraternity, the research fraternity can have a complete understanding of the provisions of structurally safe, particularly earthquake resistant safe buildings. I once again thank the organizers for organizing this event, and I wish the event and the delegates all the success and an eventful day. Thank you so much.
Thank you to all the participants for their enthusiastic and innovative presentations, and each of you showcased brilliant ideas and fresh perspectives on earthquake engineering. After careful evaluation, our jury has finalized the results, and I would please request ma'am to announce.
Thank you, Divyani. At this outset, before we come to the conclusion, I would like to appreciate the efforts that have been put up by the students. So may we have a big round of applause for the efforts. And also to the organizers for thinking that we should organize such an event. Young minds can come up on the stage and they can present their work. And I think after the 3 presentations today, all the young students who are sitting there, so maybe we can have them on the stage next time, so they get the inspiration that they should do good work. And then next year, when the Seismic Academy organizes another event, so they are here to present the work. And so after the careful evaluation and keeping in mind the work which is done and to appreciate the efforts, so what we've decided, jointly what we've decided is that we're going to have the joint winner. And the joint winner that we're going to give it is to Abhir Dutta from Jadavpur University and Sema from IIIT Hyderabad. So they both are the winners. Maybe ask them to please come on the stage. And to appreciate the work which has been done by Samved Patel. So we are going to announce him as the runner-up. So you are also welcome on this stage, and we can have a big round of applause for these young minds for doing the problem, identifying the problem statement, working on it, and finally coming up to the stage. So thank you very much, and a big congratulations to our young minds.
I would request Mr. Pulkit Kukreja to kindly felicitate the winners. I would also request Mr. Pulkit to please felicitate our juries, Dr. Shilpa Pal and Dr. P.C. Ashwin Kumar.